Ever since the dawn of civilization, humans have been looking up at the sky in awe of what we see. Some saw gods when they looked up at the sky, such as the ancient Egyptians, who worshipped the sun god Ra. The Maoris of New Zealand saw the souls of heroes when they looked up at the night sky, and the ancient Iberians believed the stars to be golden nails holding up the ceiling of the universe. Even Homer, the epic Greek poet, firmly believed the stars to be carried in chariots across the night sky. With the stars being one of the few constants that connects the history of everybody on Earth, it is difficult to imagine a time before them, or a time after them. But there once was a time where our sun didn't look like our sun. At one point, the molecules that make up our sun lived inside a giant cloud of gas and dust. All stars are born from one of these clouds, called protostellar nebulas. Over time, the hydrogen molecules in these massive nebulas are pulled together due to its gravity. As the nebula starts to collapse in on itself, it becomes progressively hotter and denser, and these hydrogen molecules start to stick to each other. At this point, a protostar, or a star still in its infancy, is formed. Once the temperature reaches 15 billion degrees, nuclear fusion begins to take place within the cloud's core. In simple terms, nuclear fusion is when two atomic nuclei combine to form a different atomic nucleus. This reaction releases an incredible amount of energy. In the case of main sequence stars like our sun, the energy they release is due to the fusion of hydrogen into helium. The reason we are able to see the stars at all is because of the radiant energy that is released due to this reaction. As a protostar grows out of this nebulous nursery, it will find itself to be somewhere along the main sequence, meaning that it falls in line with the temperature-luminosity relationship we observe when plotting stars along the HR diagram. Cooler stars will live longer lives, hundreds of billions or even trillions of years, because it takes longer for these smaller, cooler stars to use up their hydrogen supply. For hotter stars, their lives are much shorter, sometimes only a few million years. Because these hotter stars are also larger, there's more pressure being exerted on their core, causing fusion to occur more rapidly, and therefore their hydrogen supply will be depleted a lot sooner than a smaller star. Once a star's hydrogen supply is depleted, its core becomes unstable and contracts. As this contraction occurs, the outer layer of the star expands and cools. This process signifies a star entering into its red giant phase. Red giants are not main sequence stars, as they have a low surface temperature but an incredibly large surface area, causing them to be very luminous. Although all the hydrogen has been used up in the star's core, fusion continues to take place as helium fuses into carbon. Our sun is currently on the main sequence and is expected to reach its red giant phase in about 5 billion years. In this computer simulation, we can see what that may look like as the expanding star engulfs our Earth. The life that a star will lead after its red giant phase is highly dependent on its mass. For a low-mass star, its death begins after its helium supplies have been depleted in its core and the core collapses. After this collapse, the outer layer of the star is expelled to form a planetary nebula. What remains of the former star is its core, in the form of a white dwarf. White dwarfs are not very luminous despite their white-hot temperature, which lets us know that they have a relatively small surface. Typically, they are around the same size as our Earth, but have the mass of our Sun. The death of a high-mass star, however, is more violent. A high-mass star will die in a brilliant explosion called a supernova, which is so luminous that it can shine just as brightly as the entire galaxy in which it takes place. If the remnants of this explosion are relatively small, 1.4 to 3 times the mass of our Sun, what remains is called a neutron star. Neutron stars are small and extremely dense, containing as much as double our Sun's mass, but only having a radius of a few miles. The neutron star gets its name because its core is composed of neutrons. No stable atoms can exist under this extreme temperature and pressure. If what remains from a supernova explosion is greater than 3 times the mass of our Sun, however, a black hole can be formed. In this case, the remaining core of the now dead star experiences a force of gravity so great that it overcomes the degeneracy pressure that prevents protons and neutrons from combining. The core is therefore swallowed by its own gravity, forming a black hole. A black hole is defined as an object whose escape velocity equals or exceeds the speed of light. An escape velocity is essentially the velocity that an object needs to be traveling in order to break free from another object's force of gravity. Therefore, nothing can escape a black hole, not even light. There are 2 types of black holes that are known to exist. The first are stellar black holes, or low-mass black holes, which, as previously stated, are the result of the collapsing core of a very massive star, but are, however, relatively smaller than the second type of black hole known to exist, supermassive black holes. These type of black holes, while not only a great Muse song, are the largest black holes known to exist and are located at the center of galaxies. Black holes have a few known characteristics, one of them being the singularity. The singularity is at the center of a black hole, where there is essentially a rip in space-time. Space-time can be described as the joining of the three dimensions of space, which is everything 3D that exists in our universe, such as you and me, with the fourth dimension of time. The singularity completely breaks down the third and fourth dimension, so that you can no longer describe it as really existing in a where or a when. At this point, there is no volume yet infinite density. If you couldn't already tell, the laws of physics don't really work in the singularity as they do in the rest of our universe. The boundary that surrounds the singularity is called the event horizon. When something passes this event horizon, it is past the point of no return. The more massive a black hole is, the more distance there is between the singularity and the event horizon. Studying black holes may give us a glimpse into what occurred during the Big Bang, as modern theorists predict that the initial state of our universe may have been a singularity. Unlike humans, the universe is pretty good at recycling its cosmic waste. As a star dies, it projects enough gas and dust out into space to produce a new star nearly as massive as itself. Material projected from star death is processed into a dense core within a galaxy's molecular clouds, and this is where a new star can begin to emerge under the right conditions. Star death not only creates other stars, but also nearly everything else in our universe. It is because of star death that all known elements have either been created or disseminated, including the elements necessary for human life. During a star's lifetime, it produces some of the lightest known elements in our universe, such as helium. Heavier elements, such as carbon and iron, two essential elements to life, are created near the end of a star's lifetime, after it has used up its supply of lighter elements. Finally, the heaviest elements, such as plutonium, are created under the chaotic conditions of a supernova explosion. Stars may seem to be an arbitrary constant in our existence, something you take for granted each time you look up at the night sky. But if you look at your life on the cosmic scale, it was stellar death which gave the universe the tools that allowed you to be born. Okay, thanks for watching! Lifecycle.